All right, so week number 12, program verification. I look at the Google Doc. There's only one question by Amir. Let me just handle that first, and then I'll open the floor to everybody to ask any questions related to the lectures, either week 12 or in the previous week. Okay, let's read the question together. It's more about the rationale for using the Hoare triple and also proof that it's actually a tautology. Why are we doing this? Okay, it's just to clarify the context. Let's read the question together and then I'll explain. So we definitely talk about how you can prove the Hoare triple, and Amir is thinking that it's actually more important to find out what's the proper precondition and also postcondition. And then the idea is to prove the correctness, but who is going to prove the correctness of this particular Hoare triple? I would say there are two issues over here. Number one is coming up with the Q and R over here. They are not conflicting with the idea of proving the Hoare triple. So they are not conflicting ideas. It doesn't really mean if you want to do Q and R appropriately and then you don't do the proof, or vice versa, right? You should really try to do both together. Okay, let's think about what's going to be the workflow for you. Okay, think about it goes like this. You start with your source code. So you have your source code, which is more like a program. And here, even though I'm going to write down the syntax in IFO, but the idea about program verification or program correctness, you can definitely apply that to any other programming language, once you have the contracts. Let's say over here in your source code, let's say we talk about if you got a routine, R, okay, and then you have some contracts. Basically, you got require, and also you got ensure. So this is where you can put the contracts. So let's say require, we simply say Q, and ensure we say R. Yeah, and then you can also have your implementation, okay, in the do block. In this case, let me just say S. And of course, in the lecture, we say that the programming statement here can be arbitrarily complicated. Okay. So now, in order to really understand the rationale of using the Hoare triple, think in this way. Think about before we talk about this particular lecture over here, we actually say that for your precondition and postcondition, you should really try to test your contracts, right? So we are really talking about testing. And I would argue that testing is really one of the most important jobs you really have to do, even though you're only the developer, but at the same time, you should be responsible for the correctness of your code. Pretty much like in the projects and also in the lab, that we actually expect you to write some test cases yourself to really make sure your program is not just going to pass the starter test that we're giving to you, but you can also pass many other test cases. Okay, and however, there's a major limitation for testing. It's only the major limitation. The limitation is you only have a finite number of test inputs. Sometimes this might be okay because maybe if you actually choose a good enough representative set of input values to test your software, in that case, maybe you can really catch pretty much all the bugs. But sometimes it may not be good enough. So that's why we also want another approach to really complement the testing, basically, right? So now what we really want is the rationale. Is really to. So why do we also want to study the Hoare triple and also prove it? We want to complement testing, which we know is actually incomplete. Okay, limitation. And for those of you who might be interested, I think there's a fourth year course about software testing. And that way, in that course, you will learn about the various strategies for testing. But I'm pretty sure in the course, your instructor will tell you that even though you can do software testing, there's no formal guarantee that you can test all the input values. It's simply not possible because the combination of input values that can be passed to your program, we talk about realistic program, is simply unbounded. So you just cannot do thorough testing theoretically. So that's why sometimes having some formal proof will be very useful. Okay. So the way we do it, as you study the lecture, is by basically we want to say we simply formulates. Let's say currently I'm reaching a fixed point, I'm reaching a stable point to say I want to have this particular precondition, I want to have this programming statements, and also I want to have this post condition. Okay, I really want to know if they are really provably correct together, right? So what I can do is I can formulate this into a Hoare triple. So it's going to be of this particular syntax, put some predicate here, put some programming statement here, and also put some predicate over here, right? It's going to be Q and R, and also programming statements over here, right? So once you get this, you're just going to prove whether that's a tautology or not. So you can think about proving this as a tautology is an independent task of testing the Q and R in this particular stage. So they're definitely just not conflicting to each other. They are not, right? So back to the original question there. So definitely proving the Hoare triple will be valuable, but at the same time, coming up with the Q and R in the first place so that you can try to prove if they are provably correct. So that's another task you can do. All right. So, and for those, for your information, once you go through the lecture, you will see that the very important proof condition you want to know is I want to make sure the existing precondition over here is stronger than or equivalent to the weakest precondition for the programming statement to establish the post condition, right, upon termination. And this is a very important proof condition for you, okay? And if you got any doubts, you can definitely refer to the lecture. I kind of explain the rationale or intuition behind this proof condition in detail, all right? All right, so that's about the only question I have from the Google Doc. Okay, any other questions about week 12? Okay, so can we review weakest precondition of? So Amir is asking this particular question here. So I can just use the particular example you're having. I can do that. Okay. So let's say over here, I'll just copy your example. Do you want this example here, or you want some more complicated example? More complicated. You know what? I think for the WP, I can try to do the one. I would suggest the following. At the end of the lecture over there, because it's really important for you to do the exercise first before I actually go through another example. I can go over just one of the example we did in the lecture, but that was not complete. I can do that one. But I think if you really want to practice well for the WP and also proving things, you really want to do at the end of the lecture. Let me just go to the end of the slides over here. So there is one exercise over there about proving the correctness of a loop. And for that one there, it's going to involve the WP calculation for a much more complicated example, right? That's something I would suggest. But what I would do is I can do something slightly more complicated than the assignments, okay? I can do that one there. Let's say we do this one here. Okay, let's say we do this one. So we want to know, is this particular program correct, right? That's something we want to do. I will do half of it so that you will be able to complete it yourself, okay? So that's also something you're supposed to do as an optional exercise, right? Let's take a look together, okay? Let me just put it on my tablets. All right, let's say over here. Let's say this is your program, right? So think about this part over here is the specification. So we got precondition, and also we got post condition, okay? Basically, it's simply given X and Y. We want to know which one is bigger and which one is smaller. It's a very simple program, but it does involve several things. It does involve assignments, variable assignments. It involves if conditional, and also involves sequential composition. So these are the things you should really know in order to calculate the weakest precondition, okay? let's see how we can do this one here. We did a little bit actually in the lecture, but let's try to do it again. Just go a little bit further. Okay. So the idea will be we want to know. We want to. Here's a question. Okay, let's put a question first. The question is the above program correct? Okay, that's a question. And if you're being asked this question here, you should really immediately identify what's the specification, which is a precondition, postcondition, and also what is the programming statements, right? And then you want to really formulate it into a Hoare triple. That's basically what you want to do, okay? So now, for simplicity, you can also do it in case you're asked to do any WP calculation in the quiz or in the exam, okay? So for now, I'm just going to do the following. Can I just put, let's say, this part over here? Let me use a different color for you to see. Okay. Let me say this part over here. Let me call that maybe just S1. Okay, I'm going to unfold it maybe a little bit later. Okay, and also this part over here is S2. Okay, S1 and S2. Okay. And then, so let's now formulate into the Hoare triple. So now, step number 1. Formulate the source program into a Hoare triple, right? So in that case, we're going to put x larger than 0 and y larger than 0. And then, so this is going to be the programming part. So I'm just going to put if x larger than y, and then it's going to be S1. Otherwise, it's going to be S2. Okay, and then it's okay. Let me just highlight. So these are the keywords, right? And also and over here. It doesn't really matter, but let's be complete. And then and. And then we got, what's the post condition here? It's bigger, larger than or equal to, smaller. Okay, so that's the first thing you want to do, first of all, right? Hopefully this one is not too difficult. And then what we want to do now is to actually prove it. We want to prove this as a tautology. So think about step number 0 and step number 1. Prove that the above Hoare triple is a tautology. Okay, let's think about what's going to happen here. You can think about this part over here is really Q. And this part over here is a post condition, this is R. And then the entire thing over here, right, is S. Right? So what we really want to prove is Q actually implies the WP for S to establish R. So this is the ultimate goal, you should know, right? That's something we would like to prove. In order to do this, we have to split that into 2 steps, okay? Step number 1, let's say 1.1. So 1.1, let me use different color here. So 1.1, we will have to calculate the WP, right? And 1.2, once we calculate the WP, we're going to prove the implication. So I'm just going to show you for 1.1 about part of how you can calculate the WP. And then to really prove the 1.2, either to prove it or disprove it, I'll leave that to you as an exercise, right? So let's see for 1.1 how we can do it. So now I'm just going to put it here. So 1.1, okay? So now we would like to calculate the WP, okay? And then it's going to be, okay, let me just write it down. It's going to be S, which is the entire thing over here, right? So we're just going to say if X larger than Y, and then S1 otherwise S2, and then end. Okay, and then it's going to be R, right? R is exactly bigger, larger than or equal to smaller. I would just say B for bigger, larger than or equal to S for smaller. Okay, just for simplicity, right? But of course, the quiz or the exam will be online. In that case, you can simply type it out, so it'll be much easier for you to write. All right. All right. So now, how can we calculate the WP? Basically, to calculate the WP, you have to know which WP rule to apply, right? For this one here, overall, it's really an if statements, right? You can see that it's really an if statements. If, then, else, end. So we should really apply the WP rule for the if, then, else. Assuming that you have already seen the lecture, right? If you have not, then you will have to, excuse me, you have to catch up with the lecture, and then you have to come back to this particular example. So now you have to follow this particular equational style of the WP calculation, which I also explain in detail in the lecture. So now how can I do that? So I can simply say WP rule of conditional. Okay, so what I need to do is I'm going to say either it's going to be X, so it's going to be either X larger than Y, okay, either that, or X, not the case, is larger than Y, right? So we got two cases over here. If X is larger than Y, so that means it's going to be S1, right? We're going to execute S1. And if X, it is not the case that X is larger than Y, we're going to execute S2. All right. And then for both of them, for both branches, we want to make sure upon the termination from either branch number 1 or branch number 2, we want to establish the common post condition over here. So that means we want to calculate WP to see what the condition is. So this would be if X is larger than Y, the first branch, that implies the WP for S1 to establish the post condition over here. So this part has been already gone over in the lecture. So I'm just summarizing it, just a quick review. And this one implies the WP for S2 to establish B larger than or equal to S over here. And then to really put these two together, we should really put conjunction, meaning that both, not just this branch, but both branches must be able to satisfy the post condition, right? That's why we put a conjunction over here. In the lecture, I also explained, what if you use a disjunction rather than conjunction? What will be the consequence? That's also something you would like to review. All right, so now I'm just going to do this part over here for you. Okay, the other part you should really do it as an exercise. Let's do just this part over here, right? This part here. Okay, so now I'm just going to call that 1.1.1. Okay, and then this part over here is going to be 1.1.2. Okay, and 1.1.2 will be an exercise for you. It will be calculated in a very similar way as 1.1.1. Okay, so eventually, let's just see the big picture. Eventually, you will get something here as a predicate, and also something over here as a predicate. So now the whole thing over here will also be a predicate, right? And the whole thing is just going to be the WP over here. And once you get a predicate here, you want to argue either Q is stronger than that or the other way. In that case, you want to prove or disapprove this particular implication. That's what you will have to do, all right? So that will be the exercise for you. But let's just try to see how you can calculate the WP specifically, okay? So for 1.1.1, so 1.1.1, okay, let me just switch the color. Let me use, blue has been used already, so why don't I simply use purple over here, okay? So 1.1.1, okay, let's calculate that. So it's gonna be the WP, and then we got S1. And remember, S1 is basically this particular sequential composition, right? And for now, I'm just going to use B for bigger and also S for smaller, okay, just for brevity, just for abbreviation. So now for S1 is going to be B is assigned to X. Okay, so let me just highlight it for you. This part here, right? This is the part I'm looking at, S1. So B is assigned to X, followed by smaller, which is S, is assigned to Y. And what I want to establish is, I want to establish this particular post condition, right? B larger than or equal to S over here, okay? So now, for those of you who have seen the lecture, how do I simplify this? What will be the next step? What rule should I apply? Anybody? If you haven't seen the lecture, that's okay. I guess you will have to eventually catch up. But for those of you who actually have seen the lecture, now it will be your opportunity to show. Okay? So Jiahao suggests the right thing. We want to apply the sequential composition rule. Yes. All right, let's put it. So it's going to be the WP rule. So Jiahao, why don't you try? This might be a good exercise for you as well. Why don't you type on the in the chat, what should that be? If once I apply the WP rule of sequential composition, what should that be? You want to suggest something, Jiahao, you can type and then show it to us. The result from this was after we apply the sequential composition. In this case, you're lucky because it's only one single sequential composition here. Let's highlight it here. It's only one single sequential composition. The swap program that we did in the lecture that involves two sequential composition. You can look at that in detail. I did that completely in the lecture. Okay, let's look at what Jiahao did. That's pretty good. I think that's correct. Very good. Okay, let's write it down. The idea about sequential composition, which I also explained in the lecture, is really important for you to identify the intermediate states over here, right? It's some intermediate states. We want to make sure upon the termination for B is assigned to X, this particular intermediate state should be logically sufficient for S is assigned to Y to execute and terminate so that you would establish B is larger than or equal to S, right? That's something I said in the lecture. You can refer to it again. Okay, for now I'm just summarizing. Okay, so what we should do is, so what should be the intermediate condition over here? It should be here, basically what we should really do. So it should be the WP for S is assigned to Y, and then to establish B is larger than or equal to S over here, and then for this part over here, it will just be the same, right? It's going to be WP for B is assigned to X, and like that. So now the good thing is, you really want to see what the difference is before and after. So this is before, this is after. Before, we only got a single WP. However, the programming statement is way too complicated for us to apply the assignment rule. You can think about every time, once you can get to the stage of applying the assignment rules only, that means you're almost done because you're dealing with base cases only. However, in this case, we cannot do it just yet because we got some sequential composition. That's why going from one WP into a nested 2 WP is not a bad thing because now you can see this is a single assignment and this is just another single assignment. So now we can apply assignment rule one by one, 2 times in total. All right. So what I will do is, let's do it. Okay, you can say WP rule of assignments. Okay, let's do the first one here. Let me highlight it. Okay, here. This one over here, how do we apply the WP rule for assignments? Basically, you're gonna substitute every free occurrence of S by Y in the post condition, right? In this particular post condition over here, you want to substitute every free occurrence of S by Y. That should be easy because that will be simply S will be replaced by Y. So what we'll get is, so that's going to be B larger than or equal to S will be replaced by Y. So this is what we will get, right? Okay, hopefully everybody's following. Okay, I think after this, what we will get is going to be B larger than or equal to Y. Okay, any questions so far about this assignment rule application? Okay, just want to make sure everybody's okay. All right, so after this, we got one more thing to do. So this will be WP over here. So B is assigned to X. Okay, let me move, sorry, let me just make a little bit more space over here. But we're almost done, okay. So that would be the WP over here. B is assigned to X. And then, right? So now, what should we do further, right? What we should do further is, you can see this will be just another assignment rule, okay? So now, I'm just going to make some space over here. So I'm going to write a little bit more simply. So this is just going to be another assignment rule. So WP rule of assignments, right? But of course, you got to write it more properly using the curly brackets, right? Just to make sure when TA grades your proof, they will be able to see it, okay? So now what should we do for this particular application? Well, in this case, we're going to replace, in this particular post condition, we're going to replace every free occurrence of B by X, right? So here, B will be simply replaced by X. So we got X larger than or equal to Y, right? So this is the final answer. Okay, so what's the final answer here? So you can think about for this particular part that we spoke about, for this part over here. For this particular part, well, our calculated result was X larger than or equal to Y, right? So that's the result. So that's 1.1.1. As I said before, you should really complete the exercise by calculating what's 1.1.2. And then try to see if you can simplify the entire predicate here any further. And then you can apply this particular WP, and then this will be the result over here. And then you want to argue whether the existing precondition over here is really stronger than or equivalent to this particular calculated WP in step 1.1. All right? All right. So Amir, so I think that that's a more complicated example. Hopefully that's enough for you, right? So, but you should really try to complete the exercise over here and complete the proof. All right, good. Guys, any questions? I have a friendly reminder to you, right? Friendly advice. If you don't know exactly what I'm doing, possibly because you haven't gone through a lecture just yet, but I can tell you that this will be important for you, right? As far as the lecture learning outcome is concerned. So if you can kind of follow through the idea, but I think the most detailed explanation is on the lecture videos. So you should really complete that, all right?
Hello, sir. Can I have a question?
You got a question? Yes, go ahead.
Yeah, for the AFL's WP, and in the lecture slides, the alternation 1 and 2, there's a difference because the first one didn't include Q as a like
okay,
left
which
side
slide?
of the page 18.
18, okay.
Yeah, 18.
Okay, what about it?
There's only B and no B on the left side, and then check the next slides. There's include Q conjunction with B. So my question is, what's the difference between these two?
Okay, so you can see, I kind of understand, but let me know if I'm really answering your question. I'm trying to guess. So this slide over here is only to show whenever you want to calculate the WP, you should be given some programming statement over here. And the programming statement in this case will be just conditional. And then you're given any arbitrary predicates R as the post condition. And to really calculate the WP, so you will have to break it down into two parts. One will be when B is true. The other part will be when the B is not true. In that case, you have to calculate the WP in this way, right? So this is only to calculate the WP, which is part of the step for you to prove that the Hoare triple is a tautology. Okay, let me go to the next one. Okay, so now you were asking why. In this case, we will actually get Q into the context. It is because, so now our goal is not just to calculate WP, but we basically what we want to do is we want to say, given this particular program, which is a conditional, and then we got a precondition Q, and we got a post-condition R, right? Let's say that's your that's formulated from your source program. And now the question is this program correct? So if the program is actually correct, so that means you will have to prove that this particular Hoare triple is a tautology, right? So that's why you have to put the Q into context. Does that answer your question?
Oh, then one more extensional question. If we want to prove that this program is correct, there's two ways to do it, right? One way is following this, prove it is a tautology. Another way is do the WP for the right side and show that Q can imply the WP.
So actually, to prove that this particular program, let's say this, to really prove that this particular program is correct, you cannot get around by not calculating the WP. You should always calculate the WP. Well, okay, okay. Let's say the question is, we want to know whether or not this particular source program is correct. And the approach that we show to you is, you want to formulate this particular source program as a Hoare triple. So this formulation part, I presume you're okay. So after we have formulated a Hoare triple for this program here, how can we prove that a Hoare triple is actually a tautology? And the way to do it is by, first of all, we want to calculate what's the WP for this program here to establish R upon termination. And then we want to make sure the Q is really stronger than or equal to that. You say, does that answer your question?
Yeah, I get what you mean, but my question is, are they equivalent?
They're equivalent, yes. Are you trying to say either we calculate WP like this, what's the WP for this to establish R, and then prove that Q implies that? That would be approach number one. And approach number two would be this. Maybe that's what you're asking, right?
Yeah.
Okay, they are equivalents. Yes, they are.
Okay, thank you.
So I would say in the quiz or in the exam, maybe more likely to be in the exam, if we really want you to prove if a given program is actually correct, always do the following steps. You want to formulate a program as a Hoare triple, number one. And number two, depending on the structure of the program. But let's say if the structure is simply if conditional. In that case, since it's going to be open book exam, so you can either apply the normal approach, calculate the WP, and then this part WP, and then try to prove that Q implies that. That will be approach number one. Or you can simply go to this particular logically equivalence implication, which will boil down into similar thing anyway. Either way. So are you okay with this? This my answer?
Yeah, thank you.
Okay, good. Okay, Amir got another, Emerald. Emerald got a question here. Can I repeat what can we do after finding short? So let me go back there. Okay. Yeah, it's good to be more precise over here. Okay. So to answer Emerald's question, so we already calculated 1.1.1, which is this particular predicate, right? So you can think about this particular implication is x larger than y implies x larger than or equal to y, right? You might be able to simplify this to something else, but I'll leave that to you, okay? So what's left is an exercise for you. So you want to also calculate what's the WP for this particular expression here. WP for S2, which is over here, to establish B larger than or equal to S. So once you calculate 1.1.2, it will be something maybe similar to this, something not exactly the same, but similar. So once you have done that, now overall you get a big predicate over here. You will be able to simplify that somehow further, and then use that as the WP over here. And then you want to prove that the original precondition here does prove or disapprove that the implication holds. So Emerald, does that answer your question? I hope. Good. All right. So Amir asked a question, free agent. I think what you meant was free occurrences. So free variables simply means they are not dependent on other variables. No, that's not the case. So basically that goes back to your 1090. Okay, so for example, if I got an expression here, if I say x plus y, right? So here you can see x is not really bounded by any quantifiers. In that case, this will be free. And y is also free. Okay, example number one. Example number two. If I say for every z, such that maybe 1 less than or equal to z less than or equal to 10, let's say. And let's say x and y, they are unbounded. It is the case over here. Let's say x plus y plus z, let's say less than or equal to 100. Doesn't matter. Okay, so now let's just analyze this expression here. So now what we would say is x and y, they are not really being bounded by this for all because it's only binding the variable z over here. So we will say x and y, they are free. And then the z over here is actually bounded. Okay, so you may want to refer back to your 1090 notes briefly, okay? But I think that's pretty much what you would need, right? To see what's the difference between free and being bounded, okay? Good question, all right. All right, so that's about this particular WP example that will complement your lecture, but please do try to complete the exercise over here, and then so that will actually help you prove things further, all right? Okay, guys, any more questions related to week 12? Any other questions? Yeah, in theory, we have also tomorrow the Q&A session for week 12, but in case you really cannot really catch up, understandably, we got a project due on Wednesday. In that case, so if you just study the lecture, maybe lecture slides and notes and videos by Friday and take the quiz, that'll be okay. But maybe eventually you want to make sure you study the lecture in detail, at least in the exam review session, which already released the dates to you. You can ask me that if you got further questions. That'll be fun too. Okay, any more questions about week 12 lecture? Okay, I'll pause maybe here a little bit just to see if you got any more questions. While we're waiting, Siobhan, you want to ask your question about design principle? Information hiding. Information hiding does not necessarily involve the math model, not really, but math model will be one way to achieve information hiding. But to really achieve information hiding, you don't necessarily have to use math model, okay? It's just one way to really achieve it, okay? So I would say information hiding So I believe there are two places you can review about information hiding. One place would be the iterated pattern lecture. And then also the math models lecture. Right, so these are the two lectures you may want to review if you want to know about the just review the details for information hiding. But let me just talk about it quickly, okay? Just to summarize. Okay. So for information hiding, think about pretty much you're trying to hide certain design decision. Okay, so let's say this part over here is, let's say this is your system. And then, again, in some way the split, it's kind of similar to how you will want to divide certain part of your system being open versus closed. But I would say let's not bring the complication about open-closed principle. Let's just talk about information hiding, okay? So there will be certain parts of your system over here, okay? So this will be basically the part of your system subject to constant changes. So if a particular part of your system is actually subject to constant changes, in that case, you want to hide it from any potential clients, okay? In that case, you want to hide it. So that your clients wouldn't have to depend on that. Because later on, if you change this particular part over here, your client is going to be affected, right? You can look at the iterated pattern lecture about how this might happen, right? That's in the motivating example, okay? So now this will be hidden. Okay, one typical example would be, let's say currently, what would be about the data structure you're using? So for example, let's say currently using 2 arrays to implement a database. For example, you might get maybe got keys, also you got values over here as 2 arrays. But you don't really want to restrict the supplier to only this option here. So you might the supplier should be free to really to adapt this particular implementation into something else. For example, into a hash table, right? It's more like a table with simply the key and also value, right? But making such change should not really affect any clients using your system, right? So that's why it should be hidden. Okay. Number 2 will be the design decision. Okay, design decision will be a little bit more general. You can think about, in some way, data structure is just one kind of design decision. And number 2, you just generalize it to say any kind of design decision. If you think the design decision is really hidden, the client doesn't really know about this particular design decision, you simply hide it. So they simply just cannot see it. But how do you hide it? You want to use export status. Right, so you can say feature over here, and then one way to do it is simply export it to none. So that means none of the external classes can access the whatever feature that's inside. You can think about this part over here will be some design decision you're hiding. Design decision that's hidden. However, you don't necessarily have to hide it to everybody else. So for example, you might also say, rather than just exporting to none, I can also export to maybe only a particular class X. So that's also information hiding because you're hiding from everybody else except for class X. That's also acceptable. All right. There's a very quick summary of information hiding. So basically, if you want to explain about if your particular design satisfies information hiding, you have to explain very clearly, number 1, what's being hidden. And number 2, if what's being hidden is actually is changed, what can it be changed into? For example, you might change your 2-array implementation into a hash table or map implementation. In that case, why the clients will not be affected is because these features are simply exported to none. In that case, none of the classes will be impacted, right? That's something we actually talked about in the previous lecture before the reading week. And math models is just another way to do information hiding, right? Because we said that we should really use the math models as the only way for you to write post condition. So all your post condition should be written in terms of the model. And then later on, if you change your implementation decision, in that case, the model will still be model. It's just about how the model itself is really constructed, right? That's its own implementation that's also hidden. Right, so that's the bottom line. That's a very quick summary, but you should also review iterator pattern and also math models. All right.
Yeah, so that makes sense. So do you see how in export status you said it could be X?
Yeah.
Like it could be a class. So
yeah.
What if the implementation, or what if X, like what if like you're within that class,
Mm-hmm.
and it's so like that feature is only available to that class? How would that be information hiding? Right? Because like suppose, okay, so like you're within the X class right now, and then you invoke that feature, okay, and when you invoke that feature and suppose that feature is changed later on, then wouldn't the client, which is X, like have to like,
well, basically, let's say this. If I say feature over here, let's say if I say exported to, let's say Y over here, and then I also got some feature of, let's say that's in this particular section, right? What I'm trying to say, what I'm doing here is basically who can actually access features that's in this particular section over here? Only Y. And also the implementation in X. You can think about it's more like a restricted way of saying private. But in Java, when you say private, it's really private to just that particular class. But none of the outside classes can really access the private attributes or methods. But now, when we say Y over here, we're really saying that Y can still access these features, not just X. So Shivan, is that kind of your confusion?
Makes sense now, but now suppose that feature, this feature right here, it's changed. Wouldn't that affect Y, since Y is a client, right?
Yeah, that's correct, but it might affect Y. So that's why I'm just trying to say information hiding depends on how you rationalize it. So you're right. Given that we only export this to Y, so that means if there's any changes that's happening over here, it's going to affect Y. True. However, there might be many other classes in your system. They might be not just Y, but they might be A, might be B, and also C and D. So all these client classes, whenever you make any changes over here, it's not going to affect all the other classes other than Y. So that would be the part that information hiding will be useful. You want to minimize the impact of the changes. Yeah, maybe that's the missing part from your understanding.
Yeah, that makes sense. Thank you.
Okay, very good. Okay. Yeah, so guys, the reason I want to talk about this for Shivan is because information hiding, not just for your projects. I know you might be concerned about how to address this in project, but there you go. That's how you should think of it. However, for your exam, because the exam will be comprehensive, so you should really have a clear idea about the various design principles that we talk about. One of your fellow students also asked in a class forum about the programming from the interface, but not from the implementation. I think for that one there, I do believe I mentioned that in one of the lectures, but I forgot which one. You can check when you study for your exam. But you can definitely also look up your Lab Zero notes. That's also accessible from the lectures page. You can also see it from there. That also explains the that particular design principle. All right, that's good. So guys, any more questions? Any more? Okay, I will pause maybe a little bit longer and see. Yeah, we still got tomorrow, 2:30. So if you do want to catch up with the lecture a little bit, just to see if there's any question you want to ask me tomorrow, feel free. Okay, I'll wait a little bit longer. So Amir, any more questions for you? Are you okay? Okay, I hope he's okay. Emerald, any more questions from you? Okay, no response. Okay, Jahao. Very good. Okay, good. So Jahao, any questions? You okay? All right. Nina, any question for me for lecture? All right. And Robbie, any question for week 12 or any other previous lecture? Okay, I hope Robbie is okay. Anyway, so Sabrina. Okay, Robbie, that's good. Okay, good for now. Sabrina, you okay for? Okay, very good. Okay, Shivan, any more questions from you? All right, very good. Okay, Vin, any questions? Okay, I hope Vin is okay. But anyway, so guys, okay, so since like you guys have no more question for today, that's okay. I will still be here tomorrow. Just don't forget, I kind of changed my office hour this week. So it will be 12 noon to 1:30 p.m. So you will still be there, the office hour tomorrow and also Wednesday. So if you do have questions, please feel free to drop by the office hour. And then tomorrow, 2:30, we got one more Q&A for the program correctness. So I would suggest go over the concepts, and if there's any more clarification, just come, and then I'll explain to you. All right? All right. So I think everybody seems to be okay for now. But if you want to catch up with the lecture or catch up with other whatever work you're committed to, please do so. And then I'll stop the recording now, and then I'll see you tomorrow, okay, if you can make it. All right? Have a good night, and then I'll see you tomorrow.